Okay, so this is a little lecture on Archimedes' Principle, and doing it for those that didn't quite get everything I said, and for those that missed it. Quite an important lesson. Hard for me to reproduce all the demonstrations, but I will do my best to give the crux of what was going on today. Okay, so Archimedes, pretty important individual in the history of mathematics and science. As I said today, can't talk about Archimedes without talking about his ability to use mechanical levers, fulcrums, and torques. And there's a lot of physics behind there. A lot of mathematics with geometry and proofs, and his most favorite is, of course, the sphere and the ball that fits inside itself. And, of course, the development of pi through the earlier works of rudimentary calculus. I'm not going to go into that. Let me get to the crux. Of course, Archimedes' screw, the claw that we talked about in class, all pretty fascinating things that he did for his Greek city-state. I'm not sure about the Archimedes Heat Ray. We talked a little bit about that. That's open for discussion of if that was effective or not. But certainly there's a lot of other things that he did. One of the things we talked about, which is the crux of today, was the Archimedes Principle. And that principle is very, very clear. And he developed the principle trying to solve a puzzle. He was given a problem by his king, and the king gave a certain amount of mass of gold, let's pretend it was 100 grams, to the blacksmith to make a certain crown for one of the new temples for their gods. So he gave him 100 grams of gold, and he got back out a 100-gram, let's say, gold crown. However, that crown, the king suspected, was made up of gold and possibly cheaper metals like silver, thinking that maybe the blacksmith, okay, maybe the blacksmith took maybe used 80 grams of the gold for the crown, but took 20 for himself, okay, and added 20 of cheap silver to give it the same mass. So basically, what King Hero said to Archimedes was, please, can you find out if the crown is legit, made of pure gold, but don't destroy it because it's something that we need anyway. So, of course, the very famous thing that Archimedes, we hear about folklore, is that, well, a filled bathtub, he jumped in it and he spilled out some water. He displaced some water. So that came his principle. And what is his principle? Okay, well, his principle is very simple. The Archimedes principle, okay, very clearly states that a buoyant force, that's the force pushing upward, is equal. Now, it's a buoyant force on an object immersed in a fluid, that could be a gas or liquid, is equal, I don't know why I have two L's there, but in any case, is equal to the mass of the fluid, of the water or the liquid, of the displaced fluid. Now, what does that mean? I always said it a number of times. It means if I have an object, give you a cube of, let's say, copper, and let's say that cube is 100 centimeters by 100 centimeters by 100 centimeters. Okay, for drawing. So I have a volume of, probably want to go 10 by 10 by 10. That's what I wanted to do, sorry. Okay, so I went to go 10 by 10 by 10. So I had a cube that was 10 centimeters by 10 centimeters by 10 centimeters. Okay, and so 10 centimeters by 10 centimeters by 10 centimeters, okay, would give me a cube that was equal to 1,000 centimeters cubed, which we all know is equivalent to 1,000 milliliters, which is equivalent to 1 liter. So let's pretend this space this copper takes up is 1 liter. Now, if that's true, and I drop copper in water, the water that should have gone in that space is pushing on it. And the water line goes up 1 liter. Now, we displaced a liter because copper takes up a liter of space. So where there was once water is now copper. So obviously the water line jumped up, okay, 1 liter. Now I'm showing these arrows pushing in because water wants to rush into that position. One of the demonstrations today that I showed you, okay, showed that, of course, something that we talked about, if I have a container filled with water, like our UDiometer tube, and if I sink it deeper in the line of the fluid, the deeper the fluid is, or the deeper this object goes into the fluid, the more pressure. And you should know the farther that you're under the water, the more water is above you, the pressure increases. Okay, so let me go to this drawing here. So if I've got water and I have a sphere here that I'm submerging, look at these arrows. You should know that at this position here, okay, this position here, all right, there are bigger arrows pushing up. Why? Well, because this sphere is deeper in the water. The deeper that you are in the water, the more water is above you, so the pressure is higher. When we sink the UDiometer tube deeper into the water, the pressure in the UDiometer tube increases and the volume gets smaller. As I pull a UDiometer tube up, okay, you have less water here, and of course the pressure decreases. That was a demonstration I had at Pressure Unit today. So, my friends in chemistry, very simply, okay, on this side of the ball and this side of the ball, the arrows are the same because they're at the same height. So these cancel out. If you notice, the arrows on the bottom and the arrows on top do not cancel out. The ball feels a pressure of only this height, but down here, the ball feels the pressure of this height. So there's higher pressure on the bottom. Thus, the overall force, okay, of pressure, okay, is upward. And that would be a buoyant force. And this buoyant force is equal to, guess what? The mass of the fluid that you displace. So if this is a 1 liter container, okay, a 1 liter ball, then it would be a 1 kilogram, 1,000 grams of water, because remember the density of water is 1 gram per milliliter, would go up. So again, if we look below, I have 3 objects: quarks, aluminum, and lead. Let's pretend they're all 1 liter containers. All right, they're all 1 liter containers. They all have a buoyant force upward. Makes them feel lighter of 1 kilogram. They're all displacing 1 liter. We should know that 1 liter has a mass of 1 kilogram. Now, lead and aluminum are going to sink. All right. Now, if lead has a weight is a force pushing down. Let's pretend it's 3 kilograms. Guess what? Its total weight now in water, 3 minus 1, is 2. If the lead, which is much denser, is 10 kilograms, its total mass, okay, in water is now 9. They both got lighter, 9 kilograms, but they subtracted 1 from each. Why? They both had the same volume, same waters displaced. They both got lighter, okay, but they both got lighter by the same amount because they have the same volume. Archimedes' principle is the mass of the fluid being displaced. Now the cork, okay, also has a buoyant force of 1 kilogram. They're all the same. But the cork, let's pretend its mass is 0.5 kilograms. Hello, the cork is going to float. And as I drew today, the cork is probably going to do this. The line of the water will be right here. Okay, it only needs what? Half of its volume to support 5 kilograms. So that's why it's going to float halfway up. So only what? Half of the 1 liter is necessary. So it only needs a buoyant force of what? 0.5 kilograms. Therefore, it's not going to totally submerge. It's going to float. Only half of its volume, half a liter, is 0.5 kilograms, and that will support its weight, pushing down, and you have floating. Here, not going to happen. They're going to sink. The buoyant force, okay, is not big enough. Okay? The buoyant force is not big enough to overcome the bigger weight pushing down. All right, that's essentially Archimedes' principle. All right, what do we have here? Okay, so I posed a question in class, and this is what people were perplexed about. I have, let's make that all in there. Okay, so this is what we had in class today. I had an anchor in a boat. I had a log in the boat. The boat was sinking, and we posed this question, which is a very famous question. Okay, keeping in mind that we want to know what the level of water is. Okay, and I didn't draw that too well, but we're looking at the level of water in the tank. Okay, right now the boat has a total weight of, let's say, I don't know, 10 plus 1 plus, let's say it's 1 kilogram boat. So the total weight, let's say, is 12 kilograms. Guess how many liters has to be displaced upward? Okay, you guessed it, 12 liters. The total weight is 12 liters. The boat has to displace 12 liters of boat. If it doesn't, it sinks. Okay, so the water's being pushed up right now. If the boat was taking out, the water level would drop. Okay, let's throw the log over. Throwing the log over, let me just erase this drawing here. Throwing the log over, if you look carefully, only half of it's submerged. Let's look at its values. Its volume is 2 liters, its mass is 1. Only half of it's submerged. What's half of its volume? Oh, 1 liter. So 1 liter was displaced, pushed up. Okay? And my friends, its mass is 1 kilogram. 1 liter of water equals 1 kilogram. Buoyant force upward is equal to the mass of the displaced volume. Well, 1 liter, because the density of water is 1 gram per milliliter, this is 1 kilogram of force being pushed up. Well, guess what? Its weight is 1 kilogram. So it floats. Notice it's got half of its volume to spare, only half of it. Okay, but the question remains, what happens to the level? Okay, that's the question I posed. When I throw the log over into the water, the level of the water did what? Well, when we threw it, okay, from the boat, initially the boat was pushing down, so the boat comes up a little bit, but the level in the tank stays the same. So the boat comes up a little bit, okay, probably not that much, but who cares? But the level stayed the same. Why? Well, in the boat, all of the weight pushing down, and that was, of course, 1 kilogram, was the boat was displacing it. Okay? So 1 kilogram was being pushed down. Its entire weight was being displaced as 1 kilogram of water. So 1 kilogram of water was being pushed out by the log being in the boat. I throw it off the boat. Well, guess what? 1 kilogram is still being displaced by its own volume. Okay, boat comes up a little bit, but the line level stays the same. 1 liter of water was displaced when the log was in the boat. 1 liter is being displaced when it's out. Okay, and it has more than enough volume to support itself. So the line stays the same. Okay, this is the part where it gets hairy for most people. Okay, throw the anchor. What happens to the level of the line? Of course, the boat goes up. Okay, but what most people thought is it would stay the same or go up. Okay, but actually the water level goes down. Okay, the water level goes down. Why? Well, the answer is in the boat. Okay, in the boat. Okay, all of its mass was pushing down in the boat. 10 kilograms. It was being supported by the shape of the boat. Therefore, 10 liters was being displaced. That was pushing it upward. Okay, so this is pulling the water upward because you're adding more water. Now, when you threw the anchor overboard, its volume is only 1 liter. So therefore, it's displacing 1 liter of water. Things that are dense have a high mass to small volume ratio. That's why it sinks. It doesn't produce enough what? It doesn't produce enough volume being displaced to support itself. That's why it sinks. But more importantly to the problem, In the boat, its entire mass was being displaced by water. 10 liters being pushed out. If it didn't, the boat would sink. You throw the anchor, okay, to the bottom. Okay, it only displaces 1 liter. That's its volume. So, but displacing 10 liters in the boat and displacing 1 liter is a big differential. So the boat was pushing 10 liters out when the anchor was in, but in the water, it's only pushing 1 liter out. So because it's pushing out less water when it's in the water and more in the boat, this line has to come down. If the anchor was 10 liters, okay, it would float because it would have enough volume to support itself. But if it was 10 liters, the line would stay the same. But because its volume is smaller, it can only push out a smaller amount of volume. In the boat, all of its weight was pushed down. Therefore, it was pushing out 10 liters. Okay, I hope that makes some sense to you. Okay, and that's why it goes. So the bottom line is all the weight of the anchor, okay, was being displaced by 10 liters of water. Throw it in the water, not all of its weight was being displaced. Only its volume, which was only 1 liter. Less water pushing out, the water level comes down. All right. The buoyant force, by the way, for both of these is easy. This buoyant force is 1/2 of its volume, so it's 1 kilogram. That's why it floats. The buoyant force, of course, is the mass of the displaced fluid. Okay. And by the way, total volume of the anchor was displaced, so its buoyant force is 1 kilogram also. Only 1 liter of the log was displaced. That's 1 kilogram of buoyant force because that's 1 liter of water equals 1 kilogram. So these both have the same buoyant force. The reason why the anchor sinks, it has 10 kilograms. The weight pushing down is 10 kilograms. Its buoyant force going up is 1 kilogram. So how much does the anchor weigh in the water? 9 kilograms. Do the same for the log. Log has a weight of 1 kilogram. So it needed 1 kilogram of buoyant force, which it had because half of its volume was submerged and half its volume is 1 of 2. So the weight pushing down is 1 kilogram. This is a weight force. This is the buoyant force. They were equal. Because they were equal, we have floating here. Remember, the buoyant force is determined about the volume of the object displacing. Okay? And then the last thing I did a bunch of different demonstrations to show this. I'm going to see if I can find one and play that now.
What I hope to do is I'm going to dunk this in the water. And when I do that, this weight reading will go down, yeah? I mean, I can kind of show you over here. The weight reading does go down. Would you say that loss of weight was equal to the support force? And that support force, we have a name for it, begins with BF. Buoyant force, okay? So the buoyant force can be seen by the loss of weight. Can't read that now, but read it now. Read it now, subtract the 2, there's a buoyant force, yeah? All right. I'm going to do it over here in this overflow can. But I'm going to catch the water that's displaced. And I'm going to weigh it. Whoops. This is not going to be perfectly accurate, okay? But note now what the reading is of just holding, it looks like a little bit more than 1 Newton holding up the empty cup. As I dunk this in, this is losing weight, yeah? It's because I'm displacing more and more water. There, now this has lost all the weight it can lose. This is still catching water. I want you to compare how much weight did this lose, the suspended weight, and how much weight did this gain?
Okay, so what's happening here is that this had a certain reading of mass, not in the water. Suspending this in the water, okay, made the reading go down. Down by how much? By the buoyant force. Well, what's the buoyant force? The buoyant force is the mass of the water displaced. So he had a can filled with water to the top. He dropped the object in. He's spilling over that extra water into this. So he's actually measuring the weight of water that's being pushed out. This is filled to the brim. Okay? And believe it or not, as he'll probably get to eventually in his quirky way, which I kind of like, the mass of the water that was pushed out and the new mass of the lighter being buoyed up, these both will equal the mass of it without the water. This is the buoyant force, this is the mass of the buoyant force, and this is the weight pushing down. Okay, so let's continue with what he's doing.
Do you see that they're the same? And that brings us to a very important rule with fluids.
Okay, the rule is that the mass is the same because they had the same volume. Okay?
And that's this, that the buoyant force that acts on a submerged object is numerically equal to the weight of fluid displaced by the object. Okay? I didn't say the buoyant force is equal to the weight of the object over here. No, it's the buoyant force is equal to the weight of fluid, in this case, water, displaced by the object. Okay? We see that? That's called Archimedes' Principle.
Okay. Let's show that was the greatest way to do business here. But in any case, that is essentially what I was talking about today. Hope that helped a little bit.